Welcome. I think this will be our shortest practice test tutorial in all the history of algebra practice tests. Here we go. We are getting ready for the linear functions test, and this is practice test number 2. Determine whether the relationship is a function or not. If not, show why not. So when we did these in class, we used the vertical line test, and I've got my little vertical line that I can just go around beep, 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 beep. Okay, so because I beeped twice, because the line hit 2 points at the same time, we know it's not a function. And in class, we dove a little deeper and we said, you know why it's not a function? Because those 2 points are saying when x is 1, y can be either 9 or y can be -7. And we can see when we put it in table form that it's definitely not a function. But the easy way with the graph is just to use the vertical line test. So see how it says, if not, show why? On the test, you would take your pencil and you would just draw a vertical line through those 2 points, and that says it all. It does not pass the vertical line test. So as we move along to the second graph, beep, 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 it's all good. This is indeed a function. So we don't need to do anything else besides circle yes. What do you guys think about this next one? When we take this vertical line, beep, 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 beep. No, it is not a function. And by the way, this is important to remember. That's why with quadratics, it can only be a right side up u or an upside down u, because these laying down sideways u's, these lazy u's, they are not quadratics because they're not even a function. They can't even pass the vertical line test. So that was just a little insight into another part of the test. All right, let's move on. Identify each function as either linear, absolute value, quadratic, exponential, or other. When we see a u, whether it's right side up or upside down, we remember that it's quadratic. It's a quadratic because u have quads. All right, this looks like an upside down V. We can't see the rest of the V because the graph ends at x equal to 10, but if we extended the graph, we would see that it's an upside down V, and that's an absolute value. That V is in value. And then here we see a graph that's starting off really slowly, then shooting up. Yes, I realize I'm reading from the right to the left, but we know that that is going to be exponential. Now, I've told my class that we're going to learn why these graphs look the way they do instead of learning little gimmicks to recognize them. But right now, it's just an introduction. All right, I noticed that sometimes my students would put for number 7 that it's quadratic because they see a lot of u's. No, 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 there's only one u. Ha ha ha, right? There's not a lot of u's, there's just one u. So quadratic, there'd be one u. This is other. This is actually a sine or cosine graph, which you'll learn about in Algebra 2 trig. All right, and then we know that straight lines means that it's linear, and we know this is also a version of exponential where we're going slow and all of a sudden we shoot either up or down. That is exponential. On the next part of the test, it's going to ask us to compare graph A with graph B. And the similarity, we're going to try to use these words, increasing, decreasing, and rate of change. So when I look at the similarity, I do actually see one. I'm not a fan of these types of questions. I love comparing and contrasting, but not the ones that are on this test. But I do notice for this question, look, we're decreasing. Well, really, this whole graph is decreasing. It may look like that's linear right there. It's not. It's hard to see with this graph, but it's slowly decreasing and then quickly decreasing. And then this half of the quadratic is decreasing. So we could say something like they both have decreasing parts, even though the first half of the quadratic is increasing. We can say they both have decreasing parts. Okay, what's different about them? Well, neither one of them has a crock right? Neither one of them has a constant rate of change, but they do have their own unique rate of change. It's just not constant, and definitely the exponential is going to have a different rate of change than a quadratic. And so we're just going to say different rates of change, or we can do different rocks. If you get desperate, it is okay to say one's an exponential and one's a quadratic. You have, there, it's on record. You can quote me. But try not to get desperate. Try to use the words increasing, decreasing, and rate of change. All right, let's move on to the tables, where we're looking at a mapping first, and it's asking us if it's a function. And it is a function, because when we push a 1, it connects to a 2. When we push a 2, connects to a 4. There's nothing crazy going on, like, I'm just going to add this. Wonder if we pushed a 4, and instead of a 5 coming out, a 2 also could come out. So this extra part I wrote would make it not a function, but as it is, yes, it is a function. So see how it says, if no, why not? You don't have to write anything, because you said yes. All right, for this one it says, is this a function? Well, I'm noticing something. There are two things that are standing out. First of all, I have two -3s. And this time, the -3 matches up with a 3. And the second time I see a -3, it also matches up with the 3. So that's okay. That is still a function. But here's the problem. I see two zeros. And the first time I see a 0, it matches up with the output of 0. The second time I see a 0 as the input, it matches up with a -9 as an output. No, no, no. That is not functioning, that box. When you push a 0, you better get out a 0. So that's why we say no, it's not a function. If you want to use words, you can, but you can also just say 0 goes to both 0 and to -9, and that's not okay. You could also write input, one input has two outputs. You could write words if you wanted to. If you have a difficult time with words, you can always come up to me or Mr. Matchner and say what you would like to write, and we can help you express that. But you don't even have to use words. You could just write what I wrote. Okay, classify each type of function and describe the rate of change. We've got to do the hoops. First thing to note on this practice test, just like on your real test, the input, the x values are all going to go up by 1, right? There's no skipping. It goes 0, 1, 2, 3, 4, 5. A skipping table would look like 0, 2, 12, 23, 100, 3,000. Okay, that's skipping. So when we see that we're going up by 1s, we can ignore the input and just focus our hoops on the output. So that's what we're going to do. We're going to say, what, 40 minus 33 is 7, and 33 minus 26 is 7. This is looking good so far. 26 minus 19 is 7, and 19 minus 12 is 7. And okay, so we've got a linear table. Now on this practice test, it doesn't ask you to explain why, but on the real test it is. And it's linear because it has a CROC, a constant rate of change. Another way you can say it is the hoop numbers are all the same, but the most efficient, effective way to say it is that it has a CROC, a constant rate of change. The output as it's changing is changing constantly by 7. All right, so let's look at this next one. We're going to do the hoop. 6 minus 3 is 3. 3 minus 0 is 3. So far we're like, oh man, another linear? Okay, let's wait and see. 0 minus 3, if we use our calculator, is -3. 3 minus 6 is -3, and 6 minus 9 is -3. All right, so we know that when we see the same number, but one's a 3 and one's a -3, so they're not really the same number, but you know what I mean. We're seeing a 3 each time, and 3 of them are negative and 2 of them are positive. We know that's going to be an absolute value. And the most effective, efficient way to write y is because it has two different CROCs. And when you think about the graph of an absolute value, it makes sense because it's really two linear graphs put together. That's what an absolute value graph is. So we'll have, one constant rate of change for this part of the graph, and then a different constant rate of change for this part of the graph. So you can put that it has two CROCs. And then here, let's see, we've got -45 minus a -25. I'm going to pick up my calculator because it's the end of the day, and I do not trust my brain right now to do that. All right, so I'm going to put in negative 45 minus negative 27, and I get a negative 18. Then I get a negative 27 minus a negative 13. So I'm going to get, oops, sorry, I didn't do that correctly. Really, I'm doing a negative 27 plus a 13, right? Because minus a negative is a plus. All right, so that's a negative 14. And then negative 13 minus a negative 3, that's negative 10. And then we've got negative 3 minus 3 is 0. And, oh, sorry, negative 3 minus 3 is negative 6. And 3 minus 5 is negative 2. Whew. All right. Nothing special going on here, right? It's not linear. It's not absolute value. We look for a multiplier. And at first it looks like, oh, well, maybe 3 is our multiplier, right? Negative 2 times 3 is negative 6. Negative 6 times 3 is, negative 18. So there's no multiplier because that's not a negative 18, it's negative 10. So when we know it's not linear, absolute value, or exponential, we automatically go, well, it's quadratic. But we've got to do the second hoops just to make sure. Negative 18 minus a negative 14 will be negative 4. Negative 14 minus a negative 10 will be negative 4. And negative 10 minus a negative 6 will also be negative 4. And another negative 4. So when the second hoops are the same, we know it's quadratic. And the explanation is because second hoops are equal. Okay, that's another shortcut way to say it. And remember, how many quads do we have? We have 2 quads, right? 1 on each leg. We have 2 quads, and so of course it's going to take 2 sets of hoops to get to a quad table. All right. This next question, these are skipping tables, and you will not be seeing these on the test because it makes it very difficult to see what we're dealing with when the X column, the input column, is jumping around. Like, see how it's not going up by ones, instead it's going, let's see, from negative 4 to 0 is going up by 4, and then it's going up by 6, and then it's going up by 2, then it's going up by 4. So this isn't a good table to really analyze and compare and contrast with another skipping table, though actually table B is not skipping. So let's go ahead and look at table B. We're going to make a new table A, but let's see what we have with table B. When you see this compare and contrast one, you're going to want to do the hoops. So we'll go ahead and say 8 minus 1 is 7, 1 minus 0 is 1, 0 minus 5 is negative 5, 5 minus 16 is going to be what, negative 9? Does that sound right? No, negative 11. How about that? Yeah, much better. All right. Definitely not linear, not absolute value, definitely not exponential, that there's not a multiplier, but I bet maybe there's hope for the second hoops. 7 minus 1 is 6. 1 minus negative 5 is 6. Negative 5 minus negative 11 is 6. Awesome. So we know the second table we're looking at is a quadratic table. So let's go ahead and I'm gonna make table A something like you would see on the test. So you would see something that the x values are going up by 1, just like on table B. See how these x values were increasing by 1? That's why we were allowed to do the hoops on the right side. Let's say we have, let's see, 10, 8, 6, 4, 2. And we'll go ahead and do the hoops with that as well, because that's one of the ways we can compare them. 2 minus 4, negative 2, negative 2, negative 2, negative 2. All right, let's stop and compare. The differences are pretty easy. Yes, we could say one is linear and one's quadratic, but we're really going to try to use these words: increasing, decreasing, and rate of change. So the linear has a constant rate of change, right? Each output is changing by a negative 2. Each output is going down by 2. So we can say table A has a crock, the constant rate of change, and table B does not. So that's a good way to use the vocab that they want us to use. So that's rate of change, right? Croc is constant rate of change. The similarity, honestly, there's really not much similar, but we're gonna say, oh, look. Okay, first of all, we're never gonna look at the X column, the input column. The action really is about the Y column, the output column, what's coming out from the function. And so when I look at the output column, the Y column, I see, oh, 10, 8, 6, 4, 2, we are decreasing. I'm going to look at the output column for table B. 16, 5, 0, oh, that's awesome. It's decreasing. Oh, no, it goes back up. But it was decreasing for part of the table. So this is where I'm not a fan of these questions, because to find similarity, we're going to have to say they both decrease. They both decrease a bit for a while. Okay, so that is a similarity. All right, the next one is let's identify whether they're linear, absolute value, quadratic, exponential, or other. When I see an x in my exponent, I know that's exponential. When square root, have we been looking at square roots? No, that's other. When I see a 2 in the exponent spot and there's no other exponents, I know it's quadratic because I have 2 quads on my leg, one on each leg. Once again, I know I'm heavy on gimmicks for this standard, for this unit, but soon we will dive into quadratics and you'll learn why we have a 2 up there and what that means. We know 20 is just a plain old linear. 21, it's kind of a fancy linear, but it still is linear. There are no absolute values or exponents in there. 22, because of that 2 as the exponent, that is quadratic. Same thing here, 23, there's a 2, so that's quadratic. Absolute values, we see those absolute value signs, we know it's absolute value. Uh-oh, x in the denominator, no. No, no, no. That is not, when you graph that, that's not a line. Trust me. So that's going to be, oh, excuse me, I'm so sorry. That's going to be other. When you see that x in the denominator, don't make the mistake of putting linear. It's not linear. Okay, write your own absolute value function. Don't get fancy. You can just put y equals absolute value of x. Or if you want to get a little fancier, you can put some company in there. You can, go like this. You could even go like this. Whoops. Let's make it so that it's legible. So you only have to put 1 in there. For linear, once again, you don't have to get real fancy. Something like that would do, or something like that would do. Okay? All right, I believe that's it. This is the one you guys are going to get 100% on first try. I'll see you in class.